It's raining and it's actually borderline hailing too. I think I just felt hail fall on me a few seconds ago, and it seems to be too light to really see. Um, it seems to be like very isolated. Same for the rain. So if you see any of it in this video of chemistry, then point it out in the comments. But you might not. And I don't even think I saw that fell on me. I'm okay though. It's very small hail. It's not like that baseball size hail from thunderstorms because it's like, well, not a thunderstorm. Anyway, so this chemistry video is going to be about covalent bonding. So in the last lesson, chemistry lesson 6.3, we talked about ionic bonding, and in this video, it's covalent bonding. So ionic bonding is the bonding between a metal and a non-metal. This is between two nonmetals, and the way they have to bond is a little bit unique. You see, with a metal and a nonmetal, it's pretty easy because the nonmetal just simply takes an electron from the metal, and then they attract. But in the case of a nonmetal with another nonmetal, it's a little bit more tricky because they have to share, because both of them are only really capable of gaining. And while they can lose and it says so in a chem reference table, I want you to know that while yes, they can lose electrons, they can lose electrons, but it's like it's only in this relationship of covalent bonding, and you really shouldn't get confused. So it's ionic bonding. Non-metal is always going to gain. Metal is always going to lose. Covalent bonding is about sharing. Water, for example, is a covalent bond. It's actually raining right now, so we have covalent bonds around us. We breathe a covalent bond. Oxygen, the oxygen we breathe, is a covalent bond. If there's chlorine in your pool, but it's not salt, covalent bonding in action. And there's a couple of things about covalent bonding that you need to know. First of all, why does it have to be covalent bonding? Well, if you take chlorine, it has 7 valence electrons. So the thing is that if one were to take from the other, one would have 8, but then the other would have 6. And then they wouldn't bond because it has to be mutualistic. This should be parasitic. And you need like 8 chlorine atoms to form a bond this way, which is impractical. So rather, what they do is that they share. So you have to draw the orbital notation a certain way, which I'm not at home yet, even though I should be making my way over there because the rain is starting to pick up in its intensity. While the way you have to draw your electron configuration is that you need to have the 2 isolated electrons facing each other directly. They have to face each other. When they do this, they'll form one single bond that's shared between the 2 of them, and they take turns. Now, in theory, this shouldn't work, but in practice, the speed at which they move at, which is a lot, by the way, the speed at which they move at makes it such that it always feels they're full, simply because there's not enough time. Now, if it was for an hour or so, then covalent bonding wouldn't work. But it works because they move extremely quickly, probably millions of times a second. Probably around that speed. And it's kind of like taking turns as to which is full, but again, that's how it works. When you draw a Lewis dot diagram of them, the way you draw it is that you have the 2 elements next to each other, and then the shared electrons have to be on the same side. And then each one will be surrounded by 8, but you'll have to draw boxes around them, and the overlap will have to be clearly visible as to the fact that they're sharing electrons. So, Covalent bonding is only an option if you have two nonmetals. If you have a nonmetal and a semimetal, this could be confusing because it depends on whether or not the semimetal is acting as a metal or a nonmetal. It's probably going to depend on which specific elements in play too. For example, boron and nitrogen are probably going to form an ionic bond because boron can lose 3, nitrogen can gain 3, and they'll form an ionic bond. But in a case where you have, say, boron and hydrogen, this is probably going to wind up being a covalent bond, mainly because hydrogen, you really can't steal from it. It would just be a nightmare if they were to do it that way. Ooh, it's raining quite intensely now. Anyway, so as far as as covalent bonding works, we talked about this in the halogens, which is honestly where it's the most common, because outside of that, in order to have a covalent bond, I don't know how it would work for two different elements, so this is how we get diatonic elements. But, like, for example, oxygen needs to have a double covalent bond. You have 6, so 2 electrons need to be shared. Drawing that could be a little bit more difficult, and now you need to, have to incorporate 4 dots. So, honestly, the way you draw that is a little bit different. We didn't get to draw nitrogen yet. This is foreshadowed to us, but I ruined the surprise by saying nitrogen is going to be a triple covalent bond. The thing is, though, is that nitrogen will be a triple covalent bond. You need to share 3 electrons to get them into the noble gas configuration. I don't know how carbon would work, though. You see, the thing about carbon is that it's a non-metal. It's not even a semi-metal. It's a non-metal. But the thing is, carbon has 4 electrons that it would need to gain or lose. So, as far as, this would work, it can begin to become a little bit tricky at times because of the fact that carbon, if you think about it, if one side were to take 4 from the other, then both sides would have complete valence configuration. I don't know if we're going to get into quadruple covalent bonds or whatnot, but I'm pretty sure that they do exist. Covalent bonding is important because this can define differences between the nonmetals. For example, O2 is the oxygen that we need to breathe. If we don't have access to O2, we die. But O3 is ozone, another form of it. And while ozone does do a good job in the stratosphere, blocking out UV radiation, if ozone is in the troposphere, that's actually very bad because it's poisonous to breathe. As they say, good up high, bad nearby. That's how we describe ozone, because it's good in the stratosphere, bad in the troposphere. And if you ever take AP Environmental Science, just know Unit 7 is going to focus on the tropospheric ozone, 9 is going to focus on the stratospheric ozone. So, yeah. Okay, I'm going to get going now because the rain is just at such an intense speed. My fingers are getting cold because it's not warm. It's in the mid-40s at best. It's raining intensely, and I think that my fingers are about to fall off if I keep recording. I really should have brought gloves on this walk. It's not snow, but, and you might not have seen hail, but it was definitely still something.